Integrated tests are a scam. A self-replicating virus that invades your projects. It threatens to destroy your code base, to destroy your sanity, to destroy your life. Good evening. My name is Joe Rainsberger, also known as Jay Brains. Here's how you can, well, no, that's not how you can find me. Here's how you can find me. And I want to talk to you a little bit about a deep technical problem with perhaps some surprising solutions. Now, before I get started, I would really like to take an opportunity to recognize James Grenning. I haven't seen James in a while. I went to his XP for a Day tutorial at XP Universe Conference 2001 in Raleigh, North Carolina, USA. It was the first time that I got to meet many of the people who are pioneers in extreme programming and what now today we call agile software development methods. And I feel very privileged to have had the chance to learn directly from the pioneers in this area. And one of the things that I want to share with you, I've been doing a lot of keynotes about bigger issues and about people issues and about organizational issues and about where I think the agile software development industry should go in the next 10 years. But sometimes it's just nice to remember what it was like to be a programmer and to talk about programmery things. And so it's kind of funny, I was at the Agile Testing Days conference a couple of weeks ago in Potsdam, Germany. And among testers, I am a programmer. Among programmers, I am a tester. So that's a bit strange for me. So I'm going to talk a little bit about something that sounds like it's related to testing, but is really more about design. And we'll just see how things go. So as I said, integrated tests are a scam. If I'm going to say something like this, then I should probably tell you what do I mean by an integrated test. An integrated test is any test where the success or failure, pass or fail result, red or green, depends on many different bits of interesting behavior at once. Now that's not much of a definition, because now I have to define behavior and interesting. I think we can agree on many. That one's pretty clear, I hope. And I could keep going like this forever. But the important thing is that an integrated test is any test where when it fails, I cannot point right here to find the problem. Now we know that one of the properties of good tests is exactly the opposite. It would be wonderful if every test failure was the result of a single problem, and that if I knew exactly what test failed, then I would know exactly where the problem is. Integrated tests have the opposite property, where when the test fails, we don't necessarily know where the problem is. We know the problem is somewhere in this room. Really? Nobody gets the reference. One person has seen Summer School. Thank you. Summer School with Mark Harmon. Very good film. Go see it. Now, integrated test is any test that it's a test that maybe uses some cluster of things, and somebody will fix that right away. If the test fails, then we don't know if the mistake is here, or here, or here, or maybe here, maybe here, maybe there. It's not so clear. And their value as tests is actually quite suspect. Now, it's one thing for me to say integrated tests are not so good. You've probably all seen the testing pyramid, right? And the testing pyramid says that most people, when they do testing, they get the pyramid upside down. They do most of their testing through the user interface. They do some of their testing on, let's call them clusters of modules or objects, whatever your favorite way of packaging code is. And then down here are the unit tests, the little tiny unit tests that check individual functions and answer the question, does this individual function do the right thing? And so the testing pyramid says, no, turn that all the way around so that most of your tests are of this variety unit. Some of these tests are for clusters of objects, and a small number of tests go through the user interface. And this sounds like relatively reasonable advice. And actually, I think it's good advice, but I think it misses one deep problem. And the one deep problem that it misses is the scam part of my title. It's one thing just to say, because of course everything above this line here is definitely an integrated test. If we're testing a cluster of objects, or if we're testing the entire application through the user interface, then certainly those are integrated tests. The funny thing is, I don't like this word unit, because then we have to argue about what does a unit mean. So I even prefer to get rid of that and talk about isolated tests. Isolated tests meaning tests that test an isolated part of the system. And even I'll go one step further and say I'm not interested in testing, I'm interested in checking. And if you don't know about the difference between checking and testing, then use your favorite search engine and put the terms checking versus testing Michael Bolton. No, not the singer. No, not the character from Office Space. The third one. Okay? So even in this area, we perhaps don't do that good a job of writing what I think of as isolated tests. I want to be more clear about what that means in a moment. But the big thing is not just to say, this testing pyramid says integrated tests are kind of a bad idea, so don't do it quite so often. I'm not saying that. I'm saying something much, much stronger. I'm saying integrated tests are a scam, and let me describe to you how the scam works. So, why do we write an integrated test at all? Why don't we just use isolated tests for everything? Well, I don't know about you, but I have had the experience of working in a code base. I have 700 nice, beautiful, isolated tests. Each test checks one function at a time. Everything is nice. I run all the tests. They all pass 100%, but there's a problem. We find out that this module doesn't talk to that module correctly, and as a result, we have a bug. So here we have a situation where we start up here, 100% tests pass, but there's a bug. We only find that bug when we try to run the whole system together. So, what do we do with the bug? Well, the only way we found the bug was by testing the whole system together. Somebody did some manual testing, somebody wrote some automated tests through the user interface, just by, maybe even worse, a customer found the problem, I don't know. But we have 100% of the tests pass, but there's a bug. And if we found that bug with an integrated test, well, that means that we should probably write more integrated tests. So we write more integrated tests because we realize that when we try to write only these isolated tests, it's possible that all the tests will pass, but still there's a bug. So we write some integrated tests to fill in the holes, to cover the areas where our isolated tests don't work so well. Okay, that works a little bit. So we write some integrated tests, we find some problems, and everything is fine. Now, here's the problem with integrated tests. The reason why we have this testing pyramid idea has to do with design. The benefit, the real benefit of isolated tests, of tests for one function at a time, is that those tests put tremendous pressure on our designs. Those tests are the ones that make it the most clear where our design problems are. Remember that the whole point of test-driven development is not to do testing. I know it's unfortunate that test is in the name. We've had long debates about that. But the goal of test-driven, one of the goals of test-driven development is to learn about the quality of our design. We use the theory that if our design has problems, then the tests will be hard to write. The tests will be hard to understand. It will be difficult to write these small, isolated tests to check one thing at a time. So we rely on these tiny, isolated tests to give us feedback about our design and to identify the problems. If I need to write 23 lines of code at the beginning of my test to check one thing, maybe that tells me that the thing I'm checking has too many dependencies on the outside world. That is an example of the test giving me some feedback about the quality of my design. Well, if isolated tests help us find design problems, then maybe we have the converse also being true, that to find design problems, I must have isolated tests. And it turns out to be true. Certainly in my experience and in the experience of the people I've worked with and in the experience of the customers who end up calling me to fix their problems, I see a strong correlation between a high number of these integrated tests and design problems. The issue is that these integrated tests, because they test big parts of the system and because they don't put pressure on the design, the more integrated tests we have, the less design feedback we get. And the less design feedback we get, the easier it is to design not so carefully. So more integrated tests encourage us to design more sloppily. We don't have to be so careful because the tests don't give us the pressure to improve our designs. Now, what happens when we design more sloppily? What do I mean by that? Well, it means that certain parts really strongly depend on other parts. It means that I can change something over here and then something over there magically breaks. It means that if I want to change 4 to 5, I have to find all the 4s to know that I changed them all into 5s. I'll tell you a little story. I was at a conference where my good friend Patrick Welsh was running a very simple, funny tutorial. His exercise was simple. He had a computer game. Now, the way the computer game worked, it's one of these like Connect 5 games. So you play against the computer, and you put a piece on the board, and the computer puts a piece on the board, and your goal is to put 5 of your pieces in a row, and the computer's goal is to put 5 of its pieces in a row, and whoever does that first wins. There's a problem with the game. The game is very, very easy for the computer to understand. The strategies are quite minimal, which means the computer is really, really good at the game. Actually, the computer plays the game perfectly because the game is so simple. How many of us want to play a game against a computer that can never lose? Right. So, Patrick says, I have a simple request. I want to change this game so that the computer only has to, or the human only has to get 5 pieces in a row, but the computer has to get 6. This is enough of a handicap that the human player has a chance of beating the computer. So he says to everyone, all you have to do is turn 5 into 6. How hard could it be? Here's how hard it could be. So part of the problem is that the code, of course, was outsourced to a programming contracting company who wrote all the code in, let's call it English, but all the comments in Serbian. None of us are particularly good at Serbian. So, you can imagine now we are in this exercise, we're trying to work hard. I have Bob Martin himself. Uncle Bob is my pair partner. Now, Uncle Bob and I have paired for a few hours, not a lot. But we've paired a few hours on code in the past. He kind of knows how I work. I kind of know how he works. And we sat down, and in 15 minutes, we couldn't even find the first 5. There were loops inside loops inside loops inside loops with variables like II, JJ, KK, LL, and comments in Cyrillic. I could pronounce the words, but I didn't know what I was saying. And after 15 minutes, I looked at him, and he looked at me, and we just said, nope, no more, we're leaving. Patrick, you win. It's impossible. And of course, Patrick just keeps walking around saying, all you have to do is turn 5 into 6. This is exactly the kind of problem that when we focus on integrated tests and we use more and more integrated tests, it becomes easier and easier to solve problems with designs that are hard to maintain. And it only takes a few months before you might as well just have all the code in English and all the comments in Mandarin Chinese. It will be just as valuable. If you speak Mandarin, great. I don't. I speak a little bit. I don't have a glass. See, if I had a glass here, then I could show you how much Mandarin I speak. This is a cup. It's not a cup, but anyway. So, here's the problem. 100% of the tests pass, but there's a bug. I'll put the bug out here. So we write more integrated tests. More integrated tests put less pressure on the design. So we design more sloppily. When we design more sloppily, what happens? It becomes harder to write all the tests we need. It's easier to make mistakes. Now I want to get one thing clear right now. I see here in the upper right hand corner I have written the word bug. I am not going to use that word again. Bugs are these mysterious things that happen somehow that we don't control. That's not how it works. We did it. So I'm going to call those mistakes. Because that's what they really are. So 100% of the tests pass, but we find a mistake. I guess only one. That encourages us to write more integrated tests so that we fill in the cracks between our tests. But then that allows us to design more sloppily. And when we design more sloppily, there's more of an opportunity for mistakes. Now, we make more mistakes, but we're still trying to write a bunch of isolated tests. The problem there is, of course, more integrated tests means there's less time for isolated tests. So we have fewer, I'm going to call them UTs for unit tests, even though you know and I know that's not exactly what I mean. So we have more mistakes, but fewer unit tests. What happens when we combine more mistakes with fewer unit tests? We increase the likelihood that 100% of the tests pass, but we still have mistakes. And around we go. This is what I call a positive feedback loop because the effect becomes bigger. But it's a positive feedback loop of negative feelings. Come on, guys, I know it's late in the day and you all want to go home, but that was funny. That's better. This is a positive feedback loop of negative feelings. This, friends, is the scam. The scam, if somebody were to sell you aspirin that actually gives you more of a headache, you would put this person in jail. But the people who tell you to solve the problem of 100% test passing plus mistakes with more integrated tests is giving you aspirin that causes you a bigger headache. That's exactly what's happening. That's the scam. The scam is that when we spend more of our time writing integrated tests, then we design more sloppily, we make more mistakes, we write fewer tests we could use to detect those mistakes, and then even more, the likelihood happens where all the tests run green, but there are mistakes. And in fact, there are more mistakes, which means more integrated tests, more sloppiness, more mistakes, less time for unit tests, and this continues. And it continues until eventually you email me and you say, we have 3,110 tests. They require 19 hours to run. Our quality is horrible. We shipped 37 mistakes last month. What the hell are we doing wrong? And I say, the good news is I have the answer. The bad news is, here's the price. So what do we do? Well, before even we talk about what do we do, it gets worse. Now, I was very nervous for a moment during James's talk this morning, because James gave a little bit of this next part away. But I'm going to describe it again anyway. One of the problems with integrated tests has to do with the number of integrated tests we really need. So, here we have something here, something here, something here. Each of them interacts with each other. There's 5 paths through the code here, 7 paths through the code there, 3 paths through the code there. How many tests do I need if I can only test all 3 of these as a cluster? Come on, you know the answer. You heard it this morning. Right. Yeah, it was easier with James. You're not going to get easy arithmetic here. This is the advanced mathematics course, right? So we need 105 tests, at least, because there's going to be some strangeness about the interaction between them. So it's around 3 times 5 times 7. And if I add another object over here, here's the worst part. Now, let's say I refactor, and I introduce a new object here that now has 2 paths, and this one only has 6, but now I have this. Now I've gone to 180 tests. I refactored and I made the testing problem worse. He better be going somewhere good with this. So now in the general case, actually I have a room to write it here. In the general case, what do we have? Well, Here we have a whole bunch of layers. Let's call them layers, even though you know and I know that you're not really writing layers yet. We'll get there. And there's so many paths through each layer on their own. How many tests do we need to write? This many. Oh. And if that doesn't scare you, then you don't know enough mathematics. Let me write it a slightly different way. And if that doesn't scare you, you really don't have enough mathematics. Exponential curves are scary, right? We've all seen the magical cost of change curve, which, by the way, we know is nonsense, but we've seen it before, that the later you wait to fix a problem, the more it costs. And we know that the cost of change curve is approximately exponential, let's not say n, let's say t, in the time it takes to find the problem. Combinatoric curves eat exponential curves for breakfast. So now, when you rely on integrated tests, you are saying, I don't mind that I am going to write this many tests. Now, James made this point, so I'm going to make it again because it's very important and worth making. The problem isn't so much that you need this many tests. The problem is that you don't have the first chance in hell of writing this many tests. So how many tests are you really going to write? By my rough calculations, you will write somewhere between 1 and 80% of the tests that you need. And you don't have the faintest idea whether you're closer to 1% or 80%. Where you are on that line is blind luck. There are some testing techniques that you can use to get closer to 80%, but there's almost no chance that you'll know where you are on that curve. You'll be somewhere, the number of tests or the amount of test coverage you really have of your system, again, is somewhere in this room. And that, my friends, is not good enough. We can do better. So, imagine instead we listened to the design pressure, listened to the design feedback that this problem is trying to give us. What can we do differently? Yes, that's where I want to go. What can we do differently? So, let's consider any two of these objects talking to each other in isolation, because we're going to do the mathematics thing that if we can make it work for 2, then we'll figure out how to make it work for n, and then we'll use the principle of mathematical induction, and everything will be fine. You guys all remember that, right? Perfect. There, one person. Good. Don't worry, I'll remind you. So, here are my two objects. Now, the way that we would test this now, we know that this object uses that object, so then we know that we're going to have some tests for this guy, and we're going to have some tests for this guy, and then we'll have some tests for the interaction between these two guys. And as we've already seen, if we need 10 tests here and 8 tests there, then we're going to need 80 tests for the combination. We can try to do this a little bit better. Let's pretend for a moment that we don't really have to put these two guys together. What can we do? Well, really the important thing, let's call this guy over here S for server. Not a server in the sense of a box in a room somewhere that gets very hot, but in the generic term of I do work for somebody else. Because the guy on the left is going to be the client. So if we have a client, we have to have a server, just like if we have masters, we have to have slaves. Okay. So, client, server. Now, testing the server on its own is actually pretty straightforward. The nice thing about the server is that in this picture, the server doesn't depend on other stuff. The server is what we call context independent. At least let's pretend he is for now. He doesn't know about how he's being used. He doesn't worry about the world around him. Testing him is relatively straightforward. The client is not so simple, because the client depends on the server to do some work. Now again, if the client hard codes its dependency directly on the server, then we have the combinatoric explosion problem. Our tests go up like this, and we feel shame. Nobody gets that one. Okay, that's more of a Canadian hockey film, so I'll forgive you on that one, but it's good for you to go watch the film Slapshot. Okay? You know, it had Paul Newman in it, so it's important. Okay, so let's put something in between these guys. Let's call it, I don't know, an interface. Now, probably the programmers in the room have heard before the advice program to interfaces. And maybe you never really understood why this advice is any good. With any luck, I'm going to explain to you why this advice is good. Now, I can, with this interface, of course, an interface is just a collection of functions. That's the way it's normally implemented in any language. So if you're working in Java, if you're working in C#, if you're working, I can't think of any other languages off the top of my head with interfaces, so funnily enough. Most of the other sensible languages don't bother with this thing, but they have something called a protocol. And a protocol is like an interface. It's a collection of functions, but not their implementations. So if you go to your list interface in Java, and it has add this object returning Boolean for yes, I added it successfully or not. And it has contains this object returning a Boolean saying yes, I contain it or no, I don't. And it has size returning an integer that answers the question how many items there are. These are parts of the interface. The interface is meant to describe what can I do without describing how do I do it. And it all sounds wonderful and lovely, but it's extra work because now instead of just talking directly to the server, now I have to have this stupid interface in the way. Let's make that interface valuable. Because there's more to the interface than just the set of functions on the interface. There is something much, much, much more important called the contract. How many people in the room think they know something about design by contract? Okay, a few. For those of you who understand design by contract, I'll wake you up in about 2.5 minutes. The rest of you, please pay attention. The contract is the set of behavior of those functions. So for example, if I start with an empty list and I call add with the string hello, then when I call contains with the string hello, it must return true. Because I know that add has put the string hello into the list. This interplay of behavior between add and contains is part of the contract. It describes what is true about the interface. And what is true can be, in this state, this function should provide this result, or it can mean these functions work together this way, or it can mean something is always true about an object. So for example, in the case of a circular list, then part of the contract would be that there is no such thing as the end of the list. That if I ask for the end of the list, I never get one. There isn't one. Maybe it gives me null or it throws an exception. I can take advantage of this contract in order to say something about the way the client and the server behave together without having to put them together. Now the first part is actually pretty easy. So for example, the client will need to ask the server to do things. Now I'm even going to say now, he's not asking the server, he's asking the interface. Right? Circle is the universal UML symbol for interface. The client asks the interface to do something. Or maybe it asks a question. Either way, it's the same. So I'm going to say for now, it asks a question. So that's one thing that the client does. Now, the client doesn't just ask the server questions for no good reason. Probably the client is asking the server a question because someone has asked the client something. So think about the controller in a typical web application. So you have a controller whose job is to produce the report of how many customers signed up in the past 7 days. And so there's going to be an opportunity for that controller to ask the model interface, find all customers who have signed up since this date, and you provide the date. That find all customers who have signed up since function is on my nice interface. I don't actually care how that's implemented for now. I just know there's data in them there hills. Somewhere there are some customers, and I have some way of finding out which ones have signed up since March 22nd, 2013, and I don't worry about how that happens. Just do it. Now, the only reason why the controller will ever need this is because the web application framework intercepts some HTTP request, and it looks at the URI, and it looks at the request parameters, and it says, well, the URI says, produce this report, and the request parameters are empty, I don't care about those. And that's when the client, the controller, must ask the question, who are all the customers who have signed up since today? So, one of the things that in one of the aspects of this relationship is that the client has to ask the interface something. Either it says, please do this for me, or it asks a question. Now, there's also, on the left side, how do I handle the answers? So think about our find all customers who have signed up since such and such date. It's probably going to return a collection of customers. And as we all know, whenever we have a function that can return a collection, there are 5 kinds of tests that we should write. 0, 1, many, lots, oops. Okay? What happens if I get 0 customers back? What happens if I get 1 customer back? What happens if I get a few customers back? What happens if I get a lot of customers back? Because maybe I have to behave a bit differently when I get 2,000. And what happens if the interface blows up, if it throws an exception, if it does something unexpected? So there's another set of tests that I can write. By the way, I can write one set of tests to verify that in the right situation, my controller asks the model to do the right thing. Because today is the 25th of June, 1973, then when this request comes in, the controller had better ask the interface, find all customers who have signed up since the, whatever the hell that is, 18th of whatever I just said, 1973. I don't even remember. Apparently I'm not even paying attention to myself right now. We'll fix that. So, there's one set of tests that are designed to check, does the client ask the interface the right questions? And we do that with our good friend, the mock object. How many people here have worked with mock objects before? All right, so the basic idea, I hate the term mock objects, but it is so much a part of our culture that I have to keep using it. I prefer to call them test doubles, like stunt doubles. You wouldn't put Brad Pitt in the car driving over the cliff. You'd put the disposable 20,000 euro a year stunt person. And if the stunt person dies, we have a funeral, but we keep shooting the film. Right? So, test doubles have 2 basic ways of working, and one of them is to use what are called expectations. And an expectation would be when somebody tells this controller handle an incoming request, and if the date happens to be June 18th, 1973, I'm going to pay attention this time, then I expect someone to call the model interface, find all customers who have signed up since the 11th of June, 1973, because that's 7 days ago. So if now is the 18th of June, 7 days ago is the 11th of June, and now I can put an expectation on my interface that says, for this test to pass, the model must receive the request, find all customers who have signed up since 11th of June, 1973. So far, so good. Now, what about the other half of that discussion? How do I handle the answers? Well, then I use my mock objects again, and I create something called a stub. A stub is hard-coding an interface to return a specific answer that's convenient for the current test. So I write one test that says, well, let's pretend that my find method on my interface returns an empty list of customers. What should I do? Should I forward to this special page that says, I'm sorry, there are no customers? Should I forward to the normal page and just put an empty table? Should I forward to the normal page and it will handle some kind of nice message? I don't know. What happens if it returns 1? Well, if it returns 1, then I don't want to see a list with 1 item in it. Just take me directly to the details for that customer. If it returns 5, then give me a nice little list. And if it returns 2,000, give me the first 50 and paging. Page 1, page 2, page 33, blah, 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 39, 40. And if it blows up, if it throws an exception, then I forward to that wonderful page you have in your application that says, we're sorry, but we're having technical difficulties right now. Don't worry, one of our system administrators is handling it. We're waking him up now. If you have any further questions, please dial 0800 blah 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 blah. Right? So we can use stubs instead of figuring out how to make the model do the thing we want by deleting rows from a database table, by putting in too many rows in a database table, by cutting the cord on the network connection to the database server. We don't do any of these things. Instead, we write stubs. We say, please, just for this test, just once, don't give me any customers when I ask for them. Or give me one. Give me these 3. And that's a stub. On the left side of the equation, then, we can use expectations to verify, do I ask my interface the right questions? And I can use stubs to write tests that say, do I handle all the possible responses? And on the left side here, I like to call these collaboration tests. Some people like to call them interaction tests to differentiate them from state-based tests, right? A state-based test is just, here's an empty list, put an item, is the item there? That's a state-based test. Very simple, straightforward test we've been writing for over 50 years now, some of us. Not me. A collaboration test is a test on the left side of this line. They're written from the point of view of the client, and they're designed to answer the question, does the client talk to his neighbor correctly? A lot of people in this room probably write collaboration tests already. Probably do a pretty good job of it too. So then why is it that we're in this situation where we have, if we do such a good job of this writing collaboration tests, then why is it that we have 100% of tests passing and there are still mistakes? What could possibly make this happen? Well, apart from the fact that we are imperfect, well, you are, I don't know about me, but apart from the fact, good, a few of you are awake. So, apart from the fact that we are imperfect, that we don't do a perfect version of our jobs, you can probably guess from this lovely diagram that half the picture is missing. At least I hope you can infer that half the picture is missing, because here it is, half the picture is missing. I wouldn't draw all this stuff here just for my health. I intend to put something here. I'll do it in blue. So, on the left side we have collaboration tests whose job is to answer the question, does the client talk to the next layer correctly? But what happens on the other side? Have you ever had a situation where your collaboration tests are passing, and then you have a mistake somewhere and you do some debugging and you find out that that thing that you're talking to, that database, that web service, has a bug? Or maybe even it doesn't have a bug, but it just does something a little bit different from what you expected. So you assumed that the answer it could give you would be 23, and it turns out that it never gives you 23. In fact, it gives you 22. But you have a test that says what happens if the answer is 23, and you don't have a test that says what happens if the answer is 22. And that, my friends, is a contract problem. So on the right side of the equation, we are missing some tests. Because we do the left side well, we give ourselves false confidence. So what are we missing? What we're missing are these tests here. I like to call them contract tests. Probably by now that's not a big surprise. And what the hell are contract tests? A contract test tries to answer the question, does my server implement the interface correctly? What does correctly mean? Does the server that implements this interface respect the contract? Not just does it provide the right methods, because the compiler will probably check that for me. Or if we're working in Ruby or Python or another Smalltalk, another language where this stuff is checked at runtime, eventually we get that nice, I don't understand this message. I don't implement this method. Method missing, does not understand. Whatever the hell they call it in Python. So, on the right side, we need some tests that verify that this thing that claims to act like a customer model, or a customer repository, or a list of customers, I don't know what you want to call it. We'll fix the name later. we need some way to know that this implementation that actually talks to a database implements the interface correctly and respects the contract. So it's not just enough to know that the client can talk to the interface correctly. We need to know that the server implements the interface correctly. And you can probably guess from the arrows that I've drawn that just as on the left we have tests for do I ask the right questions and can I handle all the answers, on the right we have tests for do I try to answer and do I really answer that way. Now, the words are a bit weird, so let me just go like this. On the left side, we have a test that says, my controller had better ask the model, find all customers who have registered since such and such a date. Well, then there had better be somewhere at least one test of the database implementation of our model that says, well, what happens if someone does try to call find all customers registered since the 11th of June, 1973? Because I have a test over here that depends on that result. I have a test over here that says, I might ask that question. So I'd better have a test over here that says, here's how I answer that question. So at a minimum, I need to have, for every expectation I set on an interfaces method, I need to have at least one test that tries to run it. That tries to run that exact function with those exact parameters against the implementation of that interface. What happens if I do it to the database version? And that's the place where maybe I insert some rows into the database, I call the function, and then I look in the database and see what there is. Or I truncate the table and I call the function and I expect to get nothing back. Now, just like I need to have the corresponding tests on the top, I also need to have the corresponding tests on the bottom. Now remember, back over here I said that because our method is returning a collection, we have 5 kinds of tests, right? We all know them by now, 0, 1, many, lots. Oops. Well, I'd better have some tests over here that shows here are the conditions under which the implementation returns 0. The implementation returns 1. The implementation returns a few. The implementation returns a bunch. And the implementation blows up. So I write one test where I truncate the table, I call the function, and I verify that I get nothing back. I write one test that inserts a single row that matches. I run the function and I make sure that I get just that exact row back. I write at some point, well, how am I going to do the blows up part? We'll come back to that in a bit. So on the left side, I use expectations to answer to check, do I ask the right questions? Well, over on this side, if somebody has set an expectation for the method foo, then over here there'd better be at least one action that matches. So remember, every test is arrange, act, assert. Create an object or a few, invoke some function, check the result. The thing in the middle I call the action. If I have in my client a test that expects the function foo with the parameters 12 and 18, then I'd better have a test over here in the next layer that actually tries foo 12, 18, that's the action. Expectations in the layer above correspond to actions in the layer below. Okay, what's the other half? Well, if I'm interested in what the answers, if I'm going to make an assumption about what answers the interface might give me, then I'd better have some tests in the layer below that generate those answers. Which means that the answers up here will correspond to assertions down here. So if I stub a function to return 23, then in the test down here I'd better have a function that says assert equals 23 foo. If I have a stub up here where function throws an SQL exception, then I'd better have an assertion in the layer below that says, here's how this thing throws an SQL exception. So, expectations and actions need to match. Answers and assertions need to match. And if we do that perfectly, and you know we won't, but if we did, what would that give us? I now realize that I forgot to have some kind of a timer. Who can tell me how much more time I have? 10 minutes. That should be enough. I'll step on the gas. What if we got this right? What would that give us? So, let's take a look at our system now. Our system at some point has an entry point. The entry point is the first thing that the outside world calls that we built. It could be the front controller in a web application. It could be the main function in a command line application. It could be a simple function in a library. But at some point, we have the first thing. This is the top of our section of the call stack. Now that guy can't do everything on his own. If he did, it'd be 1.7 million lines of code and you'd never be able to maintain it. So that guy needs some collaborators. Those collaborations will happen through interfaces. Somebody is going to have to implement those interfaces. Pretty simple diagram so far. One client, two collaborating interfaces, two implementations, one each for each of those interfaces. Okay. Now, I can write a bunch of simple state-based tests to make sure that whatever functions that our entry point has, for which it only needs itself, and maybe the basic standard libraries, I can write simple state-based tests to know that that part works. So far, so good. So I have 5 now isolated tests. They run very quickly. Everything is wonderful. Now, I need to write my collaboration tests. The collaboration tests only worry about this guy, my entry point, talking to his immediate neighbors, the interfaces. I have collaboration tests here and here. I have expectations that show that the entry point uses the collaborators correctly. I have stubs that show how the collaborators can respond, and I know that the client handles those responses. And if I do that correctly, that everything above the dotted line works. Now, works just means passes all the tests we thought of. But that takes a lot to say, so I'm going to say works. So far, so good. I'm just defining what works means. If we can't think of a way it's broken, it works. Sorry, but that makes sense to me. Now, the collaboration tests are not enough. This is what most people do. So far, so good. What they do then is they skip down to the next layer. They do the same thing again and again and again and again. But they've missed something. That's why we're here. So now down here we have the contract tests. And the contract tests say, when you claim to implement this interface, those contract tests tell me whether your claim is valid or not. Because if those contract tests pass, I can depend on you. And if they don't, I'm going to use you instead. That's what the contract tests are there for. The contract tests are there to answer the question, can you justify having implements my interface? I'll be the judge of that. That's what the contract tests are there for. Now, the contract tests show that, yes, in fact, when you ask these questions, I try to answer them at all. And those answers that you're expecting, here's how I give them to you. And now, if those contract tests all pass, and as long as the questions, the expectations up here match the actions down here, and the answers up here match the assertions down here, then I know I use the next layer correctly and the next layer behaves correctly. Well, if I use you correctly and you behave correctly, then together we'll just work. We agree on how to communicate with each other. You do the right thing, I do the right thing, everyone's happy. And now, whoops. Of course, all those contract tests were really here. You were correcting me in your brain. You just were very polite and didn't say it out loud. And now everything above that dotted line works. Well, good news, my friends. This guy is going to have to talk to a couple of interfaces. Each of those interfaces is going to be implemented by some new objects. Fortunately, over here, this guy is not so greedy. He only needs to talk to one. And we can do exactly the same thing again. Collaboration tests over here show that this layer talks to the interfaces, they're collaborating interfaces correctly. Contract tests show that each of these implementations respects the contract that the client expects. Expectations match actions. Answers match assertions. And now everything above this dotted line works. Okay. Big finish. He promised something earlier about the principle of mathematical induction. Here it is, right? So we remember all this. Obviously. Right? What do you mean, close enough? Correct. If it's true at some point, and if knowing it's true about the nth layer means that it's true about the next layer, then it's true everywhere. If you want to, this is of course assuming that n can start at 0. If you want to start at 1, that's your business. Okay? So of course, n is a natural number. Okay, fine. Natural numbers start at 1. You happy now?
Yes.
Excellent. All right. What the hell does this mean? Well, it means that I can say the first layer works by simply writing state-based tests for the very first layer, which is our entry point. Now, we might have multiple entry points, but without loss of generality, let's pretend we just have one. We might have multiple trees. I don't care. If we can make it work for one, we can make it work for the others. So, we write a bunch of state-based tests here to show that our entry point does all the right things, and then eventually the entry point needs to talk to the next layer. I'm going to simplify the diagram. The lines are the interfaces, the boxes are the implementations. Once again, we write collaboration tests here. Of course, we've already written those tests. We write contract tests here. And now we know that the entire first layer of communication works. Well, somewhere down in the middle of our system, we have the same thing happening again. So let's just pick a random part of our system. We'll call that layer n. Guess what? This works. We can write simple state-based tests. We have collaboration tests to show that it talks to its interfaces. We have contract tests to show that the implementations respect the contracts. And we can do this for another layer. So we can make a layer talk to the next layer and everything is fine. I chose that layer at random. Well, if it's true at the top of the call stack and it's true from one layer to the next, one layer to the next, one layer to the next, then eventually this thing has to stop, right? Eventually we reach a point where there's nothing left to collaborate with, where the only thing that we talk to are simple value objects, string, number, date, time, amount, money. Just simple value objects that you just create, use, and throw away. And stuff in the platform, the stuff that you trust, the stuff that you don't test because it's been in use for 15 years, right? There are still compiler bugs left, but the odds that you're going to find another compiler bug are pretty low compared to what they were 30 years ago. So we're just going to assume for the moment that there's the boundary between what I call the happy zone, which is your stuff, and the ugly outside world, which is their stuff. You know, Java lives here, C#, JMS, Rails active framework, Rails active record, Rails active support. All that ugly stuff you never want to look at. And so eventually you're talking to this stuff directly. And if it's not complicated, then no problem. You just create some objects, you write some state-based tests, throw it away, and everything works. And if it is complicated, then all you have to do is put an interface right here. Write a simple little adapter that talks to the horrible outside world but implements your nice interface. And in the very worst case, this is the only thing that you have to test with an integrated test. All the other 37 layers above can talk to the next layer through interfaces, and you can use collaboration and contract tests, and everything is beautiful. And the very last layer that has to talk to the ugly outside world with its databases and its web services and all that other nonsense, that's the only point where you need to actually integrate with the real thing. So now you have what some people have called the ring architecture. Some people have called the hexagonal architecture. I like the ring picture myself. So imagine now here is the boundary. Inside is all the stuff we wrote. We like the stuff we wrote because we can control it. And when it goes wrong, we can fix it. And outside is all the stuff they wrote. And when it goes wrong, all we can do is yell into the wind. Or we have to fix it ourselves and pray that they take our pull requests. And we know prayer doesn't work, so what are you going to do? So, inside here is all the stuff we can control. Outside there is the horrible outside world. I like to call this in here the happy zone. And inside the happy zone, we start with our first little thing, and it talks to a few things. And then it talks to a few more things. And so we have all this wonderful stuff that we did, that we've talked about, where we've written all our collaboration tests, our contract tests, and eventually you reach the boundary, and this is the only thing that needs to talk to the ugly outside world, which means that at the boundary, we have this thin ring of stuff. And that thin ring of stuff is the only stuff that needs to talk to the ugly outside world. It's sort of not quite happy, not quite ugly. Those are our integrated tests. And everything inside are nice, beautiful, isolated object tests. Either they're simple state-based tests, create an object, call a function, assert equals, or they're collaboration and contract tests. Set expectations and make sure those expectations in the layer above match actions in the layer below. Make sure that the stubs in the layer above match the assertions in the layer below. And if we just do that everywhere, then when we put everything together, it just works. And the only integrated tests are at the boundary. Now, something very cool happens at the boundary. So, here is horrible outside world, happy zone. Here is the last thing that needs to talk to our good friend, the horrible gelatinous blob. No Futurama fans. Okay? Thank you very much. So, here is the last thing in our ring that talks to the horrible gelatinous blob. This is JMS, this is WS star, this is active record, this is Django. I don't know what this is, but we don't like it. Now again, I can write my integrated tests here, and that's not bad. 95% of my tests run entirely in memory. They're really, really fast. And instead of a combinatoric explosion, like James told us earlier today, we can turn multiplication into addition. And instead of needing 10 million tests, we need 1,000 or 10,000. I can probably write a good portion of 10,000 tests. In fact, you give me 10,000 tests and I can do an awful lot of damage. Harder with 10 million. Now at this point, again, we could write an integrated test and everything will be fine. And often we do this with, say, this is a database. But we can do even better, because eventually, in the ring, you're going to have a few different cases where you talk to the horrible gelatinous blob, and it's the same horrible gelatinous blob, and you talk to it more or less the same way. There's some duplication in here. And of course, because we follow the 4 elements of simple design, and rule number 2 says remove duplication, we remove duplication. Well, how do we do that? There are 2 ways. The first way to remove duplication is to find out that what these guys have in common is they all have 3 or 4 lines of code in them, and those are the 3 or 4 lines of code that really talk to the horrible gelatinous blob. And the rest is just bookkeeping. Well, I can pull those 4 lines of code out here. And now my 4 guys talk here. And this guy talks to the horrible gelatinous blob. There's something very nice about this picture, because now I can put an interface, and I can have these guys all talk to the interface, and my 4 lines of code implement that interface, and guess what? I just moved the ring closer to the horrible outside world. These 4 guys used to be in the ring and used to need integrated tests. Now the ring is here. I've put more stuff into the happy zone, and I've reduced the amount of code that needs to be in the ring using integrated tests to talk to the horrible outside world. Now the other possibility is that instead of pushing this code here, we actually pull it back. I'm not going to show you that diagram. You can draw it yourself. It's not that hard. But the important thing is I can do this just about as many times as I want. Because eventually, even here, I'm going to notice that there's a bunch of duplication inside here, and I can pull another little thing out, and I can make that ring smaller and smaller and smaller, almost as small as I want to make it. Almost. More and more tests run in memory. More and more tests check objects in isolation. More and more collaboration and contract tests. And more I'm taking multiplication and turning it into addition. So, what have I done here? With integrated tests, right, they're slow. Integrated tests almost always take longer to run because then they have to talk to databases and web services and networks and file systems and all that kind of stuff. Solid state drives are awesome and they're still slower than RAM. They're brittle. Right? Actually, no, they're not brittle. That's not what I meant. Yes, no, they are brittle. Different kind of brittle. They're brittle because a problem over here could make 37 tests fail even though it's only one mistake. Because the tests duplicate a bunch of stuff. So they're slow, they're brittle, and we have to write a ton of them. We have the combinatoric explosion problem. Compared to unit tests, smaller tests, isolated tests, which are super fast. Right? They run entirely in memory. No file system, no web service, no database, nothing. I should be able to run well over 1,000 of these per second. Remember how much damage I said I could do a lot of damage with 10,000 tests? Imagine now being able to run all the tests in your system all the time in 10 seconds. All of them. All of them. Now there's no longer an excuse. I can get very close. I can run 9,500 of them in 9.5 seconds. And if the rest take 5 seconds or 10, that's still pretty good. These tests are resilient because they are tiny. They're very easy to understand. Right? I'm going to set up this expectation. I'm going to run this single action. The expectation either passes or it doesn't. And I don't need nearly as many of them. Instead of multiplying the code path through the system to find out how many tests I write, now I can add them. I have to add a little constant. Maybe I have to add 100 tests because there's some mediation between the layers that could get interesting. But for the most part, I'm taking what was a combinatoric number of tests and I'm making it more or less linear. And this, my friends, is huge. That is a huge difference. So, what this means is that I can in fact write all the tests I need. Instead of writing more integrated tests which encourage me to design more sloppily, where I make more mistakes, write fewer unit tests, and I get into the problem worse, instead now what I'm doing is I write more collaboration and contract tests. And that actually finds more design problems. Because if your collaboration tests are hard to write, that means that your design is flawed. It means that your interactions are too complicated. It means that you need more abstractions. And that means, in fact, that you design more carefully. And when you design more carefully, then you make fewer mistakes. And when you make fewer mistakes, then you have more energy with which to write more unit tests, which means that as you have 100% tests passing, the likelihood of making mistakes goes down, and now we're in a virtuous cycle. And that, my friends, is how you beat the scam. That is how you beat the scam of integrated tests. You don't need them. I would like you to challenge you to write as much as possible 0 integrated tests to show the basic correctness of your code. And when you want to tell me how crazy I am, you know how to find me. Twitter is @jbrains, web is jbrains.ca, and email is me@jbrains.ca. I have been JB Rainsberger. Let's go home.